Hey, all you limit lovers, we are back and we're going to take this up a notch here. We're going to start to evaluate these limits analytically, which means without the aid of a graph, just purely with algebra. But just one final example here before we do so. Let's take a look at this rational function, and here's its graph. You might notice all kinds of little properties, horizontal asymptotes, vertical asymptotes, holes. And that's the goal, is that the more you really remember about your graphs, the more you can visualize what's happening, I think the more of a solid confidence you'll have in your answers about what they mean. So let's just take a look at this here. Asking for the limit of this function as x approaches 1. Now we have the graph, so of course let's just take a look. And as we approach 1, the x value of 1 from the left and the right, it's approaching this y value of 1/2. Nothing really significant going on at this spot. It's just a normal point on the graph, and that will often be the case with a limit question. The limit of this function as x approaches 5. As x approaches 5, we have a vertical, 5, not -5. 5, we have a hole in the graph. So the graph itself does not exist there, but that does not mean the limit does not, remember. And with a hole, the graph is approaching the y-coordinate of that hole, which is 7/10. As we approach -5, here's the one we're looking at here. Got a little ahead of myself. Vertical asymptote. As you approach it from the left or the right, it is going to infinity or negative infinity. So in general, we're going to say that that limit does not exist, and that is unbounded behavior. Some teachers, or you could argue that you could just say infinity, negative infinity, plus minus infinity if you wanted to say that sort of thing, but I think we're all kind of saying the same thing. The point is, how could you answer this purely with algebra, without this graph in front of you? How could you have gotten these things from this? Well, you could take a step and sketch the whole graph, but that might be a little time consuming. Or you might just say, this first limit, say as x approaches 1, if I were to just plug 1 into this by direct substitution, just take a look at what you would get. You'd get 1 minus 3 minus 10 over 1 squared minus 25, and you would get -2, -12 over -24, and that of course equals positive 1/2. I mean, that's essentially what you're getting, the y-coordinate there. So when we move to do these, that's often going to be your sort of first strategy is, let me just try to plug this number in. Maybe there's nothing special happening, and that's direct substitution. If I were to plug 5 into this, though, in part B, you would get 0 in the denominator, which is definitely something that's troublesome. But more importantly, you would also get 0 in the numerator. If you plugged in, you'd get 25 minus 15 minus 10. You would get 0 over 0, and that's a thing in limits and in calculus that we call indeterminate form. It means I don't really know what's happening. And so then I would move to say maybe this is a hole, maybe it's a vertical asymptote, but I'm going to factor this. So if you factor that numerator, you get x minus 5, x plus 2. Your denominator factors to x plus 5, x minus 5. And of course, there's a common factor that cancels. And specifically, the common factor that cancels is the one that was giving you 0 in the denominator, the one that was making this undefined. And that means you've got a hole at x equals 5. And when you plug 5 into the remaining, the reduced function, you would get 5 plus 2 is 7, 5 plus 5 is 10. That's how you got the y-coordinate of a hole. That's the answer to your limit question. So that's going to be a common thing. If you get 0 over 0, try to factor and cancel, and then plug 5 in if you can. That's kind of your overriding goal in a lot of these limit questions, is try to plug this number in. If you were to plug -5 in, you would get 0 in the denominator. But if you plug -5 in the numerator, and this is just, again, as if I were approaching this from scratch here, and this was the first question, you would get 25 plus 15 minus 10. 25 plus 15, 40 minus 10, you would get 30 over 0. You did not get 0 over 0. So this is not indeterminate form. It's still undefined, but the fact that it's not in what we call indeterminate form means we actually do know what this limit is. And just to sort of bring it home, when you look at this reduced function, you're left with a VA in the denominator. You know, that's not canceling, that's not going anywhere, and that's what we call a non-removable discontinuity. So this would indicate a does not exist unbounded kind of limit question. And that's really always going to happen if you have any constant other than 0 over 0. So if you get that just by plugging in initially, if you get some number other than 0 over 0, you can stop right there and say DNE unbounded, done. But okay, so these are some of the other kinds of strategies that you might encounter, and we'll talk about a few of these here today. So number 1 here, if you plug 4 in, I'm trying to evaluate the value of this as x approaches 4, so my first strategy is try to directly substitute. If you plug 4 in here, you will get 0 in the numerator. And if I plug 4 in the denominator, I'll get 16 minus 8 minus 8. I will get 0. And we would not say it equals 0 over 0. It's approaching 0 over 0. They make a big deal out of that in AP Calc, to not say it equals 0 over 0, because nothing equals it. But if you get this again, this indeterminate form, as it's called, it means do something else. The limit might exist. It might be a whole, or it still might not exist. But you've got to do some exploring here. You don't know anything. So we're going to try to factor this. And that denominator is going to factor pretty easily, of course. X minus 4, x plus 2. That numerator is a difference of cubes. Maybe it's been a while since you factored your difference of cubes, but remember it factors to not x minus 4 cubed or anything like that. It's a binomial times a trinomial, and remember it's a squared, b squared is the pattern, a and b being the cube roots of these two numbers. So this would be x, and the cube root of 64 is 4. So here x squared, ab would be 4x, not 8x. Sometimes people think it's 2ab. And b squared is 16. Now the signs, remember the pattern, whether it was a sum or a difference of cubes, was exactly the same, but the signs were the only thing that was different if it was a sum or a difference. And I use this phrase to help remember the signs, that the first one is the same as what you're dealing with. So this is a difference, then that means this is a difference. The second one is opposite. So if we're doing a difference, then the second one is a positive, the opposite. Same, opposite, and the last one is always positive. So this third sign is always positive. I know we're spending more time on the factoring than the actual calculus, but maybe it's been a while since you've done that. And now you'll see that x minus 4, the thing that's giving you 0 in the denominator and the numerator, cancels away. So we have a whole, or what is called in calculus a removable discontinuity, because I was able to remove that restrictive quantity. And here's what you're left with. If you don't take the time to write this step, that's okay, because the goal really is, now that I got that to cancel, now I'm going to try to plug that 4 in and get that y coordinate of the whole, which is the answer to my limit. If it's got a whole, then the limit exists, and I just need that answer. So plugging 4 into the numerator will give you 16 plus 16 plus 16, or 48 over 6, and that will give you 8. A little bit about notation here. Notice that limit of as x approaches 4 kind of stays out in front until you've plugged in 4. Once you've plugged in 4, it's gone, because you're evaluating the limit at that point. Kind of like when you have a square root and you take the square root of something, it's now gone. So limit is gone, and the answer is 8. So that's a pretty straightforward kind of example. Try to plug in, v is 0 over 0, try to factor and cancel, and then plug the number in. Number 2 here, If you plug 5 in, do a little direct substitution, you'll get 0 in the denominator, and in the top, 25 minus 30. 25 minus 30 is negative 5 plus 5. Again, it's approaching 0 over 0. That's indeterminate. Let's try to factor this puppy and see what we are left with. So that's a difference of two squares, x minus 5, x plus 5. Numerator, nice little trinomial, x minus 5, x minus 1, right? The x minus 5 cancels. And what are we left with here? Our new limit after we reduce is x minus 1 over x plus 5. Now we're able to plug in 5. 5 minus 1 is 4. 5 plus 5 is 10. Reduce our answers. 2/5. It's just a hole, and that's the y-coordinate of that hole. If I was still stuck with a VA, meaning I couldn't plug that 5 in, then the answer would be DNE, unbounded behavior. Okay, so now we've got this. So check this out. If you try to plug 0 in for x here, you get 0 in the denominator, and you get 0 here, root 2 minus root 2. That's going to give you 0 over 0. This is another indeterminate form. However, now this is not a polynomial. There's no factoring to be done. So we come up with something that's a little bit odd and we haven't normally done. But keep in mind, we're suspicious this might have a hole, but my goal is to try to manipulate this in some way to try to get that x to cancel. Whatever's making 0 in the denominator, you're hoping you can get that to cancel. So we're just going to try something a little out of the box here, and you're going to find that it works often when you have radicals, is I'm going to rationalize the numerator. Oftentimes you rationalize the denominator, but I'm going to rationalize the numerator just because it's a way to change the way this is expressed without changing the value of it. So I'm going to rationalize by multiplying by the conjugate, which is, if this is a minus b, then I'm multiplying by a plus b. And now be good with your algebra here, but a couple words of advice to, save you time. The denominator, you're hoping that x cancels. That's what we're looking for. So I'm going to leave the denominator in factored form. If I really want to distribute that x to each thing, I can do so at any time. It doesn't take that long. It's the numerator that I'm really changing around when I use the conjugate. So when you multiply this out, root x plus 2 times root x plus 2 is x plus 2. The outers and inners cancel out. And the last, negative root 2 times positive root 2 is negative 2. And now look what you're left with. The limit as x approaches 0 of 2 minus 2 cancels. You have x over x times root x plus 2 plus root 2. And what you wanted to happen, happened. That x canceled, meaning you're left with 1 over all this. And as soon as that x cancels, that means we are free to do what we wanted, which is plug 0 in for x. Because now it will no longer be undefined. I can plug 0 in for x, and that means I'm going to get root 2 plus root 2, or 1 over 2 root 2. And if our answer is a number, I still expect you to rationalize. So yes, that becomes, I know, rationalizing back, we get root 2 over 4. So if you were to graph this function, that means at 0, it actually has a hole. The fact that I was able to cancel eventually, it means it's got a hole at 0, comma, root 2 over 4. Okay, so we're moving along here. I'm trying to hit different types of examples without, going overboard here. So we've done the factoring and canceling. We've done the rationalizing the numerator bit with conjugates. And now we have another type of example, which is a complex fraction. Fractions are always issues for people working with. Notice if you were to plug 1 in, that would be my first move, but you're going to get 0 on the bottom, and 1/8 minus 1/8, you're going to get 0 on the top. So this is another indeterminate form, and we're looking to change this in some way. And what I'm hoping cancels, remember, is that the quantity in the denominator cancels, whatever's making 0 on the bottom. So you got your options, and this is really just how you preferred to handle complex fractions. If you think back to earlier in the year, maybe you like to make a common denominator with these two, put them together, then divide by this, which means multiply by its reciprocal. Maybe you like to do it the way I always did it, because it's a step or two faster, but it doesn't really matter as long as we all get there. I like to multiply the top and the bottom by the LCD of these denominators to cancel them. So I would multiply by 8, x plus 7. But if you do this to the top of the overall fraction, you've got to do it to the denominator. And now doing that, just be careful. And again, to save yourself a little time here, your denominator, I'm going to leave that in factored form. 8, x minus 1, x plus 7. I'm really just hoping that x minus 1 cancels. That's my goal here. So don't lose sight of that in all this algebra that's happening. The numerator is where things are really going to cancel, and that's what I was changing. So if you just visualize putting this to each numerator, remember, this one, the x plus 7 is going to cancel, and you're going to be left with just 8. Minus, and watch out for that negative, of course. If you multiply that to this fraction, the 8 is going to cancel, but you're going to be left with minus x plus 7. And please, now that you are at the end of Honors Pre-Calc, do not make this Algebra 2 kind of mistake where you think x plus 7 cancels. This is not factored. It's subtracting this. So you don't cancel anything that's not a factor. And what you do need to do is distribute that negative and combine your like terms. Completely simplify that numerator there. And now, yes, I'm still writing limit because I still haven't plugged in 1. I haven't evaluated the limit yet. 8 minus 7 is 1, minus x. And in all this algebra, we're getting really close to what we wanted, which is to try to cancel this. And that is super close. I'm just going to switch the order and take out a negative 1. Because if you notice, we had those just exact opposite signs, which whenever that happens means the quantities will cancel and you'll be left with a negative 1. And now you are free to plug in 1 because that part is gone. So when you plug in 1, you'll have negative 1 over 8. And when you plug 1 in for x over here to this quantity, which is still there, 1 plus 7 is 8, you will be left with negative 1/64. Graph this if you like, and you'll see that at 1 there is a hole. The graph does not exist, but it is really approaching that value, negative 1/64, whatever that decimal is. If you want to like check it on Desmos or your graphing calculator, the closer you get to 1, the closer the y value will get to this decimal value. Okay, and now what would it be without a little trig example, right? So first step, try to plug pi in for theta, and in the numerator, tangent of pi squared. The tangent of pi is 0. 0 squared is 0. When you plug pi in for secant, because remember, if I don't get 0 on the bottom, if I get 0 over 5, I'm done. 0 over 5 is 0 and move on. Not everything's going to be indeterminate, I promise you. But if you plug in pi in this case, secant of pi is negative 1. Remember the reciprocal of cosine of pi, and cosine of pi is negative 1, so its reciprocal is still negative 1. Negative 1 plus 1, 0. So yes, this is indeterminate because that's what I'm really trying to show you in this video, is how to handle a variety of indeterminate forms. This is not a complex fraction or a simple factoring, it's trig. So with trig, you got to get a little clever. You can do a few things. One thing, if you like, is trying to multiply by sort of the conjugate, if you will. It's not exactly a conjugate, I don't think, but multiplying by secant of theta minus 1. Again, just trying to change this in some way. And if any of you are thinking, hey, there was something else I could have done right off the bat, you're right. And I'll talk about that in a second. But if you do that, this time I'm going to leave the numerator in factored form. And this denominator is what I'm going to multiply out, because that's the thing that I was using the conjugate of. So that's the thing I'm looking to change. you'll get secant squared minus 1. Now don't bother to factor that as a difference of two squares and cancel, because it'll just put you right back here. But what this does allow you to do, if you didn't think of it already, is you can use a Pythagorean identity. Oh yeah, sine squared plus cosine squared equals 1. 1 plus tan squared is equal to secant squared. That old identity there. So if you manipulate that, secant squared minus 1 is always equal to tangent squared. So I'm going to take out secant squared minus 1 and replace it with tangent squared. And of course that's going to allow me to cancel that tangent squared of theta that's in the numerator. And that's good, because that is what was causing there to be a 0. And now you're left with this, which means now we can plug in. I'm trying to evaluate the limit of this, which is no longer going to be undefined, I hope. If I plug pi in, secant of pi is -1 minus 1, -2. Very nice. And if any of you were thinking about that right at the beginning, yes, you absolutely could have replaced tangent squared with the same identity of secant squared minus 1, then factored that as a difference of two squares and canceled the secant plus 1, and you'd be left with this same expression right here. So a couple of ways to get to the same spot. I know this was a bit longer of a video today, but I was just trying to show you a series of examples. So, you know, if you get stuck on one of those in particular, feel free to come back to this, pause it, rewatch it, or as always, ask questions if you have them. So I hope all is well, and I hope this is going okay. See you later, guys.